Let's start recording. Oops. Need to record here. Good morning, everyone. As you can see, this is lecture 13. It's our second lecture on continuity. I wrote that it's section question mark of tau. The stuff we're going to do today isn't really in tau, or it is in tau, it's just sort of in different places. So I'm going to encourage you to read the lecture notes, which I'm going to be uploading as soon as class is over and I have a chance to proofread them and things. Okay. Are there any questions before we get started? Okay, well in that case, so here's the warning. We're going to be doing today's limits. Tau does a very, very strange thing with limits. Tau insists that the function, he insists that the function be defined at the point you take the limit, and that its value be equal to the limit value there. I mean, so in essence, he's assuming he's only allowing you to take a limit where you're continuous. Okay. Now, I mean, I guess Tau has his reasons. I'm going to do it. So what I did in the lecture notes is I just went back to Bartow and Sherbert, what we did last semester. And I said, let's just take that and we'll lift it to the general metric space context. Okay, and that's, their handling is kind of the standard handling. And so that's what we're going to do. And it's going to have this problem where for the rest of our dealing with continuity, when you look in Tau's book, when he talks about limits, they're not the same as our limits. And they're not the problem is they're not the same as anybody else's limits either. Okay? So we're going to have lecture notes throughout this chapter. I guess I'm saying, you know, if you read Tau's book, only do it in addition to the lecture notes, and be careful because some of the definitions are a little bit different. Okay. Okay.
Dr. Dyer?
Yes.
Do you know why Tao is so, I don't know, like contrarian to the, like, so bizarre? I mean, it seems like he's doing a lot of non-standard things like this. Is there like this, like a reason to it? It just seems like it's complicating things, at least for us.
So I'm sure part of it is from Tau's perspective, it doesn't matter. You know, he's probably like, well, this, you know, who cares how this is defined, you know? There's some essential concept, and we're getting close enough to the essential concept, and blah, blah, blah. You know, I also, you know, I don't know how long Tao spent thinking about how to present the various things. Anyway, I'm just assuming he has some reason that I don't understand. But, like I said, we're going to follow Bartow and Sherbert. So, really, today's lecture, it's all stuff you've seen. You just saw it last semester, you know, and that was a while ago because you saw it maybe in September or October. And you only saw it on the real line. And so now we're going back. We're doing it in a general metric space. But again, you should recognize everything we do today. Okay? So the first thing is, if we're going to talk about limits, you remember last semester, there are only certain places where we're allowed to take limits. Let's define those. And what were those points called?
Cluster point?
Yeah, cluster points. Okay, so now our setting is we've got a metric space. And we've got a subset of that metric space. And we want to define what it means for a point to be a cluster point of that set. Okay. So your point is a cluster point of a set if and only if for every delta now I can't remember, in fact I forgot to check in Bartle and Sherbert which definition we used. There's like 3 equivalent definitions we can use for this. This time I really want to use this definition. You're a cluster point if for every delta, when you look in the set, well, how about we put it this way? When you look in the delta ball centered at the point, it contains infinitely many points of the set. So this intersection is infinite. Okay. Now, an exercise would be, so I'll write this over, I'll write this right here, that you're a limit point, oh, sorry, your cluster point if and only if there is a sequence xn from the set A minus A that converges to A. Does anyone remember which one we took as the definition last time?
I think we took the exercise version.
I'm thinking we did too.
Yeah, the one we took last semester involved the epsilons and whatnot, so I think it was more like the exercise.
Okay. Well, I don't know. That's either justification for switching it up or justification for not switching it up. But I think the infinite, the fact that you saying that the neighborhood is infinite, I think is a little bit more fitting with the kind of topological approach we're taking. Okay. So that's the definition of cluster point. It's the same as last semester, but in a general metric space. Let me just point out to you, the cluster point doesn't have to lie in the set. Okay, you can be a cluster point of a set without being in the set. Okay, so this is why, for instance, you can have in the real line, we could have a function defined at an open interval and consider its limit at an endpoint. Okay. So cluster points don't have to be in the set. And now let's just look at a couple examples because we are in a more general setting. Example 1, let's just go back to the reals. If we're in the reals with normal metric, the set 1 over n has, well, what are its cluster points? So,
0.
yeah. And that's the only one. Okay. I'm sure we proved this last semester. Just for any other point, there exists some delta so that its neighborhood only contains finitely many points of that sequence. I guess it's a set. Only contains finitely many points of that set. Okay. Now let's yes, okay, so Benjamin asked a question. I was actually going to do this after the examples. We're going to call them cluster points because we're using this definition. There's another definition of a point. There's another definition of things called limit points. The definition is slightly different. Instead of the neighborhood containing infinitely many points of the set, you ask that the neighborhood contain at least one point other than the point itself. Okay? Now, it's an exercise to show that in our setting, in the setting of metric spaces, if every neighborhood contains at least one point other than the point itself, then actually every neighborhood contains infinitely many points. Okay, and the way you prove that is, well, that one point other than the point itself is at some positive distance away from the point. And now consider a delta which is, well, less than that. And you keep doing that. You get infinitely many that way. Okay, so that definition of the contains one point other than the point itself, that is the definition of a limit point. And in our setting, limit points and cluster points are the same thing. But in a general topological space, which is not a topic we're getting into in this semester, those concepts are different. You can have a limit point that is not a cluster point. Okay, so all of that just to say that, yeah, cluster points and limit points are the same thing. And I might accidentally use the term limit point. And you're free to also use that term. I mean, because they're the same thing. For what we're doing. Okay, I hope that did a positive amount of clearing things up, not a negative amount. Okay. Now, I believe Tao's definition of limit point is also non-standard. So what I was saying was only for the standard definitions. Anyway. Got two more examples. Let's let A be an open set in, let's take our space to be R to the n, so n-dimensional space with the L2 metric. Then every point of A is a cluster point of A. Alexis raises a good question. Why are we going with the cluster point definition instead of the limit point definition. Eh. Well, in the lecture notes, there's an exercise to say that they're the same thing. So why don't you do that exercise, and then you're allowed to use whichever definition you would like. Okay. I don't know which one we should be doing. I thought the infinite intersection was. I thought the infinite intersection was maybe a little bit clearer about what's going on. Okay, for the second example, if you take an open set and R to the n with the L2 metric, then every point is a cluster point. Right? We're saying that if you take any neighborhood of that point, well, first of all, that neighborhood, maybe we should write it out a little bit. We take a point, we're in an open set in R to the n. I don't know. That's the open set, I guess. We want to show that for any delta, the intersection of the delta ball around that point with the set is infinite. Okay, well, it's not the case that the delta ball itself is necessarily contained in the set, because delta could be really big. But it is the case that there is always some neighborhood of our point that is contained in the set. And so we can find some neighborhood of the point that's fully contained in the set, and then we can shrink it a little bit more if we need to, so that it's also contained in that delta neighborhood around the point. And every neighborhood in R to the n with the L2 metric is going to be an infinite set. Okay. Okay. Now that's all with the L2 metric. Our final example. There are never any cluster points in the discrete metric, in a discrete metric space. And by that term, I mean any space with the discrete metric. So in a chat, Benjamin pointed out, it seems like the second example is dependent on us using the L2 metric for Rn. Well, it's certainly dependent on us not using the discrete metric. How about that? The L1 metric or the L infinity metric, they would both give you the same result. Okay, you just, right, and so now I'm talking about the previous example. Depending on your metric, you might have to look at squares instead of circles, or diamonds instead of circles, but you're still going to get the same thing. However, if you use the discrete metric, then there are no cluster points. Okay, and you can just look at the definition and see how there can't be cluster points, because if we're in a discrete metric and we take delta equal 1/2, then that set that we're supposed to look at, if we have delta equal 1/2, that set will contain at most 1 point. Okay? Because it won't even necessarily contain A itself, because A doesn't need to be in capital A. So it'll have at most 1 point. Okay. Questions about cluster points? AKA limit points. Okay. First result. Always do that. Our first result is that continuity comes for free at non-cluster points. Okay, so I'm going to write the whole thing out. It takes a little bit of practice to figure out what we have to write out to get the setting correct for these results. So we're going to talk about functions, so we need two metric spaces. So let x and y be metric spaces. And suppose the point A in X is not a cluster point of X. Okay. Then every single function f from x to y is continuous there. Okay, so like I said, at non-cluster points, continuity is free. Okay, this is just an exercise in, well, you got to look up the definition of continuity, and you've got to negate the definition of cluster points. Okay. Continuity says for every epsilon, there exists a delta, such that if the point is within delta of A, then the function value is within epsilon. Well, not being a cluster point means there exists some delta such that the only point within distance delta of A is A itself. Okay.
Dr. Goddard,
Yeah.
is it my intuition says no, but just to be sure, if we're not a cluster point in a larger set, we're also not a cluster point in a subset? Because, you know, maybe you could cut off the non-cluster point parts of a set. I feel like you can't do that, but I just, you know. And then in this definition, we're assuming the whole metric space, or this proposition, can we take subsets as like a subspace to fit subsets? So the function is going from x to y instead of like some subset of x.
Right, okay. So your first question, right, if we take a subset, yeah, if we take a subset, we're not going to make something into a cluster point. If you look at the definition, I mean, it's about neighborhoods being infinite. So a subset is going to shrink the neighborhoods, if anything. Yeah, in this result, then it points out I'm taking the entire space to be the domain of F. The reason I'm doing that is because I need the function. You need the function to be defined at the point in order for it to be continuous there. Right? You're not allowed to be continuous somewhere you're not defined. So I need the function defined there. What we could do Well, I mean, so we could introduce some domain so that we're not talking about functions defined on the entire metric space X. But whatever we wrote for this proposition, where we introduce some kind of domain, would not actually be more general. Because no matter what kind of ambient metric space you're inside, you can just restrict that metric space to the domain of F. Okay, and then you can use this proposition. Does that answer your question, Daniel?
Yes.
Okay. So yeah, I mean, I guess every result when we're proving results for metric spaces, remember, you can always restrict the metric space. And that's a thing you have to do quite often to get the full use out of these results. Okay, so we prove something about metric spaces. That means, you know, the metric space doesn't have to be the whole real line. It can be just the domain of your function. Okay, you can always restrict the metric space. Okay, well, we're halfway through. We need to get to limits. So let's define them. And it's exactly the same definition as last semester. Except now we have a function between metric spaces. And we have some domain, which is a subset of the metric space. And we've got some limit point of that domain. Cluster point is what I'm trying to use today. And then we have some value of the limit. Okay. So A is a cluster point of the set, capital A, and B is some value in the in the codomain. And now we're going to define what it means for the function f, which maps from A to Y, to have limit B at the point A. We're going to write this exactly how you'd think. If and only if, and now just epsilon delta. So remember what limit means in the real line. It's the same thing here, but with general distances. And so for every epsilon, there's a delta such that the distance between the function value and the purported limit is less than epsilon whenever the point and the point where we're taking a limit except now I have to be careful. Remember this part, we are not allowed to consider the point where we are taking the limit. And there we go. So I hope everybody sees this is pretty much exactly our definition from last semester. Remember, you're not allowed to have the point be distance distance 0 away from A. And what that means is you're not allowed to actually consider what the function is at A. Okay. Now, as you'll see, rest of the lecture, we're going to do some results about limits. I believe they're all things we did last semester, just lifted to a more general context. But some of them are going to be stated a little bit differently. So pay attention for that, and try to connect them to what you remember from last semester. Okay, and feel free to jump in if there are any questions on this definition. For our first result, just limits are unique. We proved this last semester. I'm not going to prove it this semester. The proof's the same. Suppose that it had two limits. Well, so first of all, just a general thing about proof techniques here. This is one of those where you're very tempted to argue from contradiction, but there's actually a slightly nicer way to do it than contradiction. Suppose it had two different limits, say b and b prime. Well, you're actually going to derive the fact that the distance between b and b prime is 0. And therefore, by our metric space axioms, b has to equal b prime. Okay. Or if you want to argue by contradiction, fine. The distance between them is positive, and then what would you do? You'd choose that epsilon to be smaller than half the distance between them, so that no value of f of x could be within epsilon of both of them. Okay? Anyway, I'm going to leave that as an exercise to prove that limits are unique when they exist. Another result we're going to leave as an exercise that we did at some point last semester. This takes a while to state, but all it really says is if you've got a limit at a point, then if you go and you define your function to be the value of that limit at that point, you've made your function continuous at that point. Okay. Or another way you can think about it is if you happen to have a removable singularity, or I guess I should say removable discontinuity, then if you fix that removable discontinuity, you become continuous there. Okay. So now, how do we state that in our context? Well, we've got two metric spaces. We've got a domain in X, and we've got a cluster point of that domain. Now, our hypothesis is going to be that we have a limit there. And our conclusion is that we can fill in the limit, we can fill in the function value to be equal to the limit and get a continuous function. Now, I'm going to define a new function. Let me leave the rest of that line unfilled for now. And write the definition of G. Okay, anywhere except A, we want G to just be defined the same as F. At A, we want to define it to be equal to the limit of F there. And then this is continuous. Okay, and I left a little bit to be filled in. Okay. Now what goes there? Well, here's the thing. F might not have even been defined at A. So in the domain of G, we want to make sure that A is there. The way we make sure that A is there is we look at capital A union A, take that to be our domain of G. We get the same codomain, and then we finish that sentence. Okay. Wouldn't it, Benjamin asked, so wouldn't it be better to say that it's continuous at A instead of just saying it's continuous? Well, yeah, I mean, what I wrote is false. Thank you for catching that. Yeah, the at A is critical. It's not, it's not continuous everywhere, that's for sure. Not necessarily continuous everywhere. Okay? Okay, this again is just chasing definitions, so I'm not going to prove it here. I do want to point out, we pointed out that since G has to be defined at A and F doesn't have to be defined at A, we we insist the domain of G be written as A union A. Now, that doesn't imply that little a isn't in capital A. Little a could be in capital A, in which case that domain is just capital A. Okay, we're just making sure it's there. We're not somehow saying that it wasn't there to begin with. We're saying in case it wasn't there, make sure it's there now. Okay, the other thing I want to point out, we're talking about this function g of x, but we're not claiming that g of x is not equal to f of x. It could be the case that f of x was already defined at little a and equal to its limit at little a. In which case, what this proposition is saying is that f is continuous at little a. So that's almost even more useful than saying we can fill in removable discontinuities, is saying just that if the function f happened to be defined at little a and its value at little a was its limit at little a, then it is continuous at little a. Okay. Any questions about that result? Okay. Now we come to the result that I actually sort of intended to prove, but I don't think there's actually time for this one. But for this one, there will be a proof in the lecture notes. For the others, I have left them as exercises in the lecture notes. Okay. I went back, for this one I actually went back and looked at Bartle and Sherbert. This is exactly their term for this result, the sequential criterion for limits. Okay. So it tells us how to convert a limit of a function to a limit of a sequence. Does anyone remember how it goes?
Isn't it for every sequence in the domain that converges to the value of interest, there's a the sequence of the image of those values converges to the limit.
Yeah, exactly, except that we have to take the sequence to be in the domain minus the point. Right?
Okay.
The sequence is never allowed to be equal to the point where we're taking the limit. But yep, that's it. It's just going to take us forever to state, because we have to do all this setting the table here. We got our two metric spaces. We've got a domain in X. And we've got a point where we can take a limit. So A is a cluster point of capital A. So the limit of the function f, whose domain is A and whose codomain is Y, at this point A, exists and equals B if and only if, and remember, whenever you see an if and only if, you know, that sort of means you can take this as an alternative definition if you want, right? It exists and equals B if and only if for every sequence xn from the domain minus the point at which we're interested that converges to A, sequence of function values converges to B. Wow, okay, that's a lot. Okay. Like I said, the lecture notes are going to have a proof of this. You can also just go back to your notes from last semester and look at the proof we gave then and translate it. You know, in one direction, if you suppose that the limit of f at A is equal to B, and then you take the sequence, then the sequence is going to get close to A, and the definition of limit is going to force the function values to get close to B. That's one direction. For the other direction, you want to go with the contrapositive, and you'll prove if f has a limit at B that's not, sorry, a limit at A that's not B, then you can make a sequence. Right, no, we don't have to say that. We'll say if the limit of f at A either doesn't exist or isn't equal to B, then we can construct a sequence that converges to A for which the sequence of function values does not converge to B. Yeah, Benjamin raises a good point. This definition will never be vacuously true. There will always be some of these sequences because the definition of a cluster point forces sequences like this to exist. If you've got a cluster point, you can always make a sequence xn that satisfies these hypotheses. Okay, we've got 1 minute left. I want to give, again, this is another one from last semester, just translated. And this is the sequential definition of continuity, or the sequential criterion for continuity. Okay. Because I only have 1 minute, and you'll get the formal statement in the lecture notes, let me just remind you informally what this says. F from A to Y is continuous at the point A, and here, note, sometimes in this lecture, the point little a was inside capital A, sometimes it's not. The difference is that you can take a limit outside your domain, but you cannot be continuous outside your domain, okay? You're gonna be continuous at a point, you gotta be defined there. So here, your point has to be in the domain, and I should say it has to be a cluster point. Okay, again, you'll get the formal statement in the notes. This is if and only if for every sequence xn from A, from the domain. And now, notice we don't say the sequence can't equal A, it can now. And you remember what our condition is. The sequence of function values must converge to, to B, to f of A. So continuity is the same thing as take any sequence in your domain, going to the point, your sequence of function values at that sequence has to converge to the function value at the point. Okay. Well, that's our lecture on kind of going back and redoing limits from last semester. I hope you'll agree that really nothing changed, just we added a ton of hypotheses to everything because we had to insist on all these things.